So every measurement has an uncertainty associated with it, and quite often when we do some kind of calculation, we combine measurements. We want to know what the uncertainty is on the total of the final result. And we can do that using tolerances given by the manufacturers. We can also estimate it by taking replicates for a particular measurement and getting the standard deviation. This is useful, or can be useful, for experimental design. If there's more than one way to do a particular operation or do a particular analysis, we might want to compare the tolerances to see which one is the most precise method. Just to give you a simple example, let's say we were interested in making a dilution, so we want to make 0.12 molar hydrochloric acid and 500 milliliters of it. And we're going to start with something which is exactly 12 molar. So we're going to ignore any tolerance for the 12 molar hydrochloric. The way you would do that is just to rearrange the dilution equation for V1. So we know that our final concentration is 0.12, and our final volume, we want 500 milliliters, and we're starting with 12 molar, and that's going to give us 5 milliliters. So what that means is, in practice, what we would do, if we want to get this as precise as possible, we'd use a 500 milliliter volumetric flask, Class A glassware, and we would put some water in the bottom. We would add 5 milliliters from a transfer pipette, we'd mix it up well, and then add water to the line to get the 0.12 molar. So let's say we want to find out what the uncertainty is on this concentration, this final concentration that we're trying to measure. The way you would do that is to look at the measurements, the tolerances of the particular measurements. So if we're using a 5 milliliter transfer pipette, the tolerance on that is plus or minus 0.01 milliliter. And we're using a 500 ml volumetric, so the tolerance on that is 0.2 milliliter. So how do we combine those? Well, this calculation involves multiplication and division. If you're trying to calculate the final concentration, it would be C1 times V1 over V2. So you're multiplying and dividing, so we have to use those rules. And in general, if you have multiple operations and you follow through the rules for propagating uncertainties in the same way or in the same order as you do the calculation. So in this case, we're just multiplying or dividing, so we can use our rule for multiplication and division, which is in terms of relative uncertainties of the measurements. We're going to square the relative uncertainties and add them up, and then square root the answer. That will give us the relative uncertainty for our final result. So in our case, the 5 ml pipette has an absolute uncertainty of 0.01 milliliters. We divide it by 5, the units cancel to give you a relative number. We square that. And then for the volumetric flask, it's 0.2 milliliters over 500. Again, we square that and we square root the result. And that gives us our overall relative error. And we do that calculation. 0.01 divided by 5 is going to give us 0.02. We square that, we get 4 times 10 to the minus 6. And then if we do 0.2 divided by 500, gives us 4 times 10 to the minus 4. We square that, we get 1.6 times 10 to the minus 7. Add those two numbers up and square root, and we end up with a relative error of, just do that quickly, and square root the answer, 0.020. That's a relative error. Now we know that the actual result, our final concentration, is 0.12 molar. So to get the absolute error, which is really what we're interested in, multiply that 0.02 by 0.12, and we're going to get 0.0024, and the units of that are molarity. Let me write that again. Okay, so our absolute error is 0.0024.